On va commencer.
Tu mets ton.
Ah oui, il faut que je mette mon headset.
Ben, c'est bon. Les horloges,
Yeah. Ouais. J'ai plus de batterie là. Ouais, mais je vois, il clignote low battery. Bon. Au revoir. Okay, so we are going to start on time. So I'm going to present the a new extension of the Faust language called On Demand. This extension is the result of some discussion we had nearly 2 years ago on the Faust mailing list. People discovered a hidden primitive called enable and start to use it to control when computation were done or not done, etc. So it was a very experimental primitive, and we always thought it was not the right way to do that. So on demand is hopefully the right way to control when computations are done. So basically, the traditional way to see on demand is that you have some circuit, and you want not to compute every sample, so you send the demand to the output, and the output send the demand to its own argument, so to speak, until you reach, for example, the real audio inputs or sensors inputs, etc. And then the computation can take place. So this is equivalent to so, for example, in Super Collider, they have this kind of thing, but you need to use special UGens. So the challenge here for Faust is to use the normal Faust semantics. So basically, the observation is that doing on demand is like doing normal audio computation on sampled signals, which is what you have here. So the idea is that to have a new primitive that take an Faust expression, a Faust circuit, and transform it into an on-demand version by adding an input for a clock to control this computation. So basically, the clock is a signal containing only ones or zeros, and when you have a 1, you want to do a computation, and when you have a 0, you just maintain, so to speak, the outputs without doing any computation. So if your clock is just the one signal, something which is always 1, this is like doing not having any on-demand. So what I would like to show you, so we have a problem that maybe you can see the whole slide like this. Okay, so what I want to show you is the specification of how the compiler will work for that. It's really the specification that we are using to implement the new compiler. There are way too much slides, so if you want to see the details, I will skip many slides. So, but you can find the slides on GitHub, and if you want to look at the details of the specification. So basically, this is how the Faust program, the Faust compiler works. You start with the Faust program. This Faust program is evaluated, and you have a kind of audio circuit, so to speak. The Faust program, a flat circuit, so to speak. And then we need to discover what this circuit is doing by doing a symbolic propagation of signals inside the circuit, so that we get the output. Each output signal as an expression that depends on all the input signals. And then we will translate these signals into instructions. I will explain what are these instructions. Then you will schedule these instructions. Then you will have several backends that generate code. And finally, you end with imperative code. I'm not going to describe the scheduling itself because it was described 2 years ago. And I will only concentrate on the specification of these three elements. Okay, so let's start with the Faust circuits. So basically, there is a concept of circuit, the concept of signal, and the concept of instructions. For each of these objects, I can give an syntactic description as object of this element, and then a semantic description. So for the circuit, if you look at how you build a Faust circuit, basically you have integer user interface elements, numerical operations, and then you have the 5 composition operations, and then the new on-demand operation. So on-demand is an operation not on signals, but on signal processor, on circuit. Obviously it's a simplification of what a Faust circuit is. We don't have read-only tables, read-write tables, waveforms, audio files, etc. But it's only what really matters for specifying the compiler. Okay, so I will use a lot of these inference type rules, which seems to be scary, but they are super simple and a very convenient way to describe what is done. For example, if here, so these are the rules to say that Faust circuits are well-formed expressions. So basically say that if you have a sequential composition, you want the outputs of C1 to be equal to the number of inputs of C2. That's all what is said here. So it's suppose that C1 has M input and N outputs, and suppose that C2 has N inputs and P output, then C1 sequentially composed with C2 has M inputs and P outputs. So it's super simple, really just a very convenient way to describe things. Okay. Oh, so. Yeah. Non, bah, je sais pas si quelqu'un peut.
Je peux mettre le son à fond, ça suffira.
Il y a des piles là.
Il y a des nouvelles piles. Okay, so sorry for that. So, I hope. So now I'm going. Now that we know what the Faust circuit is, we are going to describe the semantics of a Faust circuit. So basically, it takes input signals and produces output signals. The rules, again, are super simple. I skip this one. Let's go, for example, to this one. So what this says that if you have a numerical operation on signals in Faust, this operation, the result is a signal that apply this numerical operation. Thank you so much. A signal that apply this numerical operation to the samples of the signals, of the input signals, and produce the samples of the output signal. Okay, so here what we say that if we have a delay operation, the result is the signal delay by the first signal delayed by the second signal. So it's straightforward. The only complicated things is when you have recursive expressions. So I'm going to describe a little bit what happens with recursive expressions. So basically, if you have C1 tilde C2, so you start by creating a fresh identifier, here W, and you propagate inside C2 W1, W2, etc., the different projections. So W is a collective name for a tuple of signals. And then you have individual projections for each of these signals inside this tuple. So W1, W2. So what you propagate is W1, W2, etc., delayed by one sample, because this is the semantics of how the tilde operation works. you get some result here. You concatenate this result with the input signals of C1 tilde C2. You obtain some results. And these are the results of the outputs of C1 tilde C2. But also you can use the first Q signals are as definition, recursive definition of W. Okay, so everybody's lost, or is it okay? More or less. Well, yeah, you are doing category theory, so don't. So it's okay. And so the other interesting point is the on-demand semantics. So basically, what does it mean to do on-demand on a circuit? Is that you have this C circuit, and you send to C the downsampled version of S1, S2, etc., downsampled by the clock signal. You get some results, and you upsample the resulting signal, and this is the semantics of on-demand of any circuit, circuit C. Okay, so now I can define what are signals in Faust. We need to extend the definition of signals to support upsampled and downsampled signals. So basically, this is the grammar of signals. You have numerical operation, delays, and downsample and upsample signals. So this is the syntactic description of the object, but you have also the semantic description of the signals. So a signal is a function of time. In any Faust signal, when you, the value, so it's from Z to R, and the value at time t before 0, it's always 0. So this is an important property of any Faust signal. So we just have to describe what happens when t is greater or equal to 0. So if you have a number in Faust, it generates a signal which is this number, and this signal here produce sample value that are this number starting from t0, but not before t0. Again, before t0, all the values produced by a signal are zeros. Okay, so then you have the inputs, you have recursive definition. So basically on the recursive definition, look at the definition and you ask the definition what is your value, etc., etc. Because there is always a one sample delay. At the end you will end with negative value, so you know it's 0. So it's always computable. And then you have these two upsample and downsample, and upsample definitions. So let's start with downsampling. What does that mean to downsample? It means that you have a signal S1, you have a clock signal here, and this clock signal contains ones and zeros. So basically every time there is a 1, you keep the sample, and every time there is a 0 in the clock signal, you just discard the signal. So the result of S1 downsampled by S2 here is A, then D, then F. And here, in order to compute this, it's convenient to create a kind of auxiliary signal called down of S2, which basically compute the indices of S1 that of the sample that will be kept by this operation. So this is what is described here. So you see here down of S2 is just the set of all the indices where S2 is equal to 1. So the semantics of S1 downsampled by S2 at time t is the semantics of S1, but not at time t, at time the value of down of S2 at time t. For upsampling is a little bit different. Here upsample means that you have this short signal and you want to maintain, so to speak, between the clocks the current value. So whenever you have a 1, you take a value from S1, and whenever you have a 0 in S2, you maintain the previous value of S1. So again, you can compute a set of all the indices that will be kept. Okay, well, it's not a problem if you don't understand right now what's going on, but anyway, you have those slides. So now that we know the semantics of samples, signals, including upsampled and downsampled signals, we can implement the compilation itself. So basically the idea is to translate all the signals as a set of instructions. And these instructions are made of 3 different elements. Because now we are not going to do the instruction every sample. So we need to introduce a kind of time reference that describes when this instruction needs to be computed. And this is this part here. And then this instruction basically is the idea to store in memory some signal. So you have a destination and then you have a signal expression. We have 3 different categories of instruction: scalar instructions, vector instructions that are used for delay lines, for example, and this special instruction here to compute the current time in the current time reference. Voila. So what is a time reference? Well, basically it's a list of signals, of clock signals. So imagine at some point you have a circuit, it's embedded into different on-demands, and so there is a list of all the clocks of all the surrounding on-demands. So this is the time reference. So note here that instead of the signal are from a set M, because it's a variant of the signals that we call memory signals, that are signals simplified to access to memory. So you don't have delay lines, you don't have upsampling and downsampling anymore, but memory destination or memory sources. So basically, when you want to upsample something, it's just that the signal is computed, it's stored into memory, and then maybe you are going to read this memory quicker than it is updated. So this is basically upsampling and downsampling can be just done, at least in this framework, just by reading memories. So we need to have memory signals, so that's what I just tried to explain. These are signals, but all the upsampling, downsampling, and the delay lines are replaced with operations of reading and writing operation, well, reading operation in memory. Then there is the translation process itself. To do this translation, we need to be able to create identifiers. So the idea is that, and you need to compile things. You cannot just compile an expression per se. You need to compile an expression inside a time reference. And so you need to find a way to give names to for scalar memory, variable vector memories, etc. And for recursive signals, you need to be able to mark them. So when you compile code, the result of compiling a signal in a time reference is a memory signal, that is a signal but where all the upsampling, downsampling were removed, and a set of instructions. This is the way the compiler works. So for number user interface inputs, you just have a memory signal, you don't have instruction, there is nothing to do more than that. Then when you have you compile a numerical operation on signals, Then you compile all the argument of this operand, you collect all the instruction, and then you merge all these instructions together, and you create a new memory reference for this signal operation in memory. When you want to do upsampling, okay, so you want to do upsampling, so you have S1 upsampled by S2 into some context temporal reference T. Then you should compile S2, the clock signal itself. Then you compile S1 not in the time reference T, but in the time reference combined with the clock signal itself. And you get this. You create identifiers, and then you mix all, you do the union of all the operation sets of this the compilation. Downsampling. Downsampling is a little bit different. If you are downsampling, it means that you end at the input of an on-demand that was downsampled. So you need basically to compile. You were compiling S1 downsampled by S2 into this environment, and now you are compiling S1 into this. You pop up basically the time reference that was added by the on-demand. So because now you get out of the on-demand, so you pop up this part of the time reference. Okay, so for delay lines, what you do, you compile the signal, you compile the signal used for the delay, you create an identifier, and then you a vector identifier, and then you add an instruction that store the signal into the delay line, and the expression that you return is the expression that read the delay line. And for recursion, well, it's scary. Well, you have two cases basically. Is it your first time you meet the recursion, or have you already met this recursive signal? Well, you will have to look at the slides in more details. Well, the easy case is obviously when it's the next time you visit. So the first time you visit, you mark and say, okay, I'm already visiting, so because you want to stop the recursion, you don't want to visit again. So basically this is the mechanism of marking. And then you have a global compilation function. You basically you say, okay, I have my circuit. My circuit produces a tuple of signals, and now I'm going to compile all these signals. And by default, we are in the time reference 1, which is the time reference where the signals are computed at every sample, basically, because we are not in any on-demand at the root level, so to speak. Okay, let me give you some examples. So the new primitive is called on-demand. Currently there is an experimental compiler that knows how to draw the block diagram and know how to generate instruction, but are not really linked for the moment with the various backends. So what's interesting here is that you see that on-demand of underscore, it's a sample and hold. So you don't have to make sample and holds in the complex way that we did before. Just by the on-demand of the on-demand version of identity function, it's a sample and hold. If you look at how the code is generated, here it is. So now for each instruction, you have potentially a condition or a set of conditions that depends of the various clock signals. Okay, so what happens now, here it's interesting because you have the same program, underscore, but with different conditions. So in this case, you cannot just compile and share the code because it happens in different time conditions. So the code is, you see, generated in two separate stream of instructions, so to speak. But if you share the same input and the same clock, then obviously again the code is combined and only one version of the code is generated. If you have something like this, so we have an integrator here, we integrate one, and we have an on-demand version of that. So it means that every time the play button is pressed, the counter will increment, and will stop to increment when you stop pressing the button. And this is the code that is generated. Well, all this example shows that we have the right property, that when things need to be really separated, they are separated, and when they can be shared, they are shared. Okay, so you can look at the various examples. So just to conclude, what's missing, again, we don't have all the primitive, the nice primitive like table, waveform, etc. We will have to replace at some point the interval computation. We have to do that for Faust. We have to do that for several reasons. Currently, the compiler doesn't use this instruction to generate the C++ code, so this is something we have to do. And after, when we will have a prototype that passes all the tests, we will have to merge that with the normal Faust branch, which is going to be quite tricky. There are future extensions that are interesting. So you see, our previous attempt to do multi-rate in Faust were attempts where we tried to introduce some new primitive on signals. But it turns out that this was not the right way to do that. Basically, Faust is a language to describe signal processors, and all the operations should be not on signals, but on signal processors, so to speak. So the idea with on-demand is to have a new operation on signal processors, but we can imagine to have several others. For example, interleave. Let's say you have FFT with, I don't know, 128 inputs and outputs. By doing an interleave, you will wrap this into a new circuit with one input and one output, which has the interleaved samples that will feed the signal of the FFT. So it's a very simple way to do multi-rate and to do FFTs, because we know how to write an FFT in Faust, and the only problem is that we don't want this FFT to be executed at every sample. Probably using the same technology, we can do up sample and down samples. Just more convenient than using on demand to do that. And also with this technology of instructions, we will be able to, we'll try to do some data parallelism. Currently, it's very easy to find all the parallelism in a Faust program, but it's not necessarily efficient if you have a limited number of cores. And moreover, we don't exploit the SIMD instructions. We let the compiler, the C++ compiler, do that for us. So the idea here is to be able to find a technique to find more easily data parallelism and introduce data parallelism. To see that, okay, we have the same instructions applied to different data, so we can vectorize the data of these same instructions and separate after the result. Okay, so basically this is it, and it was in 29 minutes. So sorry, it's probably a little bit not complex, but too much information in half an hour. But yeah, you have the slides if you want. Are there any questions?
Where are the slides?
The slides are on GitHub.
Someone asked on the chat.
Yes, here at this address on GitHub.
Okay.
Yes, Tanguy.
I missed something about the delay.
Mm-hmm.
So when you have a delay in a time reference, what is the clock which is acting on the delay?
So it's the clock of the time reference.
So it means that you have to be careful how you write delays. If you have downsampled by 2, a delay of 1 means 2.
Exactly, yes. This is one reason why we should introduce a downsampling version, because maybe in some case, if you need to know that the sampling rate, you can have the sampling rate of a Faust program, but in this case, if you have libraries with filters, etc., you want the sampling rate to adapt to the current time reference, so to speak. If the time reference is just an on-demand with sometimes some ones, some zeros, there is no way you can define what is the sampling rate. But if you do downsampling, then you can do that. So it's even if the same core technology, it's useful to have a downsample operation per se.
And for upsampling,
So basically, upsampling is like having a clock where instead of 1 and 0, you may have 4 and 0. So you can really generalize that, but it's useful to put more constraint for a buffer size and this kind of stuff. It's useful to know that you are upsampling by a fixed factor, more than having a more general clock. Well, we need to test, but this is my current idea.
so but basically it will be coded into the clock signal itself. The fact that by having 4,
Yes.
you say you want to upsample
Yes.
by 4.
But yes, you know that you have a clock which is always 4.
Yes.
And that you know that if you need to look at the sampling rate, you can multiply by 4 the sampling rate. So, okay. So, thank you. So the next talk now is, who's next? Ah oui.
Direct HDMI?
I do, yeah. Yeah, it seems to work.
You try to
Unplug and restart maybe.
maybe you have to downscale the resolution.
Should I just
do you already have this problem? No, because
no,
it
no.
seems to come from
yeah,
computers.
from this before.
If it's a Google Doc, maybe we can.
I can share with someone.
Yeah.
Can you make-
C'est un slide après le capture sur un
Ah oui.
ça va se voir, je pense.
Ah oui. Ah oui, ça marche. You want to try on my computer?
Ah, sure, yeah. I do, yeah. Oh, sure, yeah.
This is
Okay.
Yes, yeah.
Here, you sure? This one? Nope.
Oh, that's strange.
That's good.
You are on Windows or
No.
Linux.
on Linux?
Yeah, I'll share. Try to see.
Yes. You will have a French keyboard. Is it a
Yes,
problem?
no. What's your email so I can?
Orlarey, O-R-L-A-R-E-Y, at gmail.com. Okay. Okay. You want to
Full screen.
full screen? So probably affichage, diaporama, the first one.
Got it. Okay, hi everyone. Sorry about that. Okay, running late, so I'm just gonna dive right into it. Hi everyone, my name is Jamie, and I'm here to present my work on static performance analysis of Faust programs using data flow modeling. And so, just for starters, I just wanted to motivate the work that we've been doing on facilitating Faust programs, static analysis of Faust programs. So we're seeing a trend where systems on chips are becoming increasingly available to us. And when I say that, what I mean is that we're seeing an increasing range of affordability that kind of accompanies an increasing range of processor capabilities and specializations. And as a result of that, we're seeing that it's really becoming quite viable for almost anyone to be using these systems on chips in any of their projects. But what we're really interested about with this is how they're being used in real-time audio signal processing programs. And so just below here, I just have some examples of there's the Pi block, and it's a shield for the Raspberry Pi, and also to be used for as a media interface and an audio interface. Below that, we have the Rebel Technologies owl pedal, and that runs on a STM32 for microcontroller, I believe. In the middle block, we have the Empress Effects Zoya, which is a reprogrammable synthesizer and effects pedal. And just below that, we have the Cornell, which runs pure data on Raspberry Pi as well. On the far right is an interesting one. It's a reprogrammable cello, I believe, called the Neural, and it runs Super Collider, and has a bunch of sensors that the artist uses for sonification, as well as to charge. I think it's some like solar panels to charge it, which is quite interesting. But the whole point of all of these examples is just to show that that reprogrammability is becoming like a big thing. It's becoming quite a common feature in many of these products, and at the same time, SoCs are being used in the design of many effects and digital musical instruments. And so while this is all very exciting, there are still some challenges to be faced. And it's that there are some barriers to entry to programming modern SoCs. The first being that it's difficult to know, buying these SoCs costs money, and it's difficult to know exactly what kind of processors you need for it. The second thing is that writing real-time audio DSPs in C++, for example, can be quite a challenge. And so, especially when you have some performance constraints to be met, and you have to hand optimize your code, and that's just not a particularly enjoyable experience. And so, on top of that, if you add like the issue of having to implement these things on different SoCs, and it becomes quite a challenge. And lucky for us, Faust actually addresses many of these issues. And it does so by facilitating real-time, the writing of real-time audio signal processors. And so what happens is that users don't really need to have much of an expertise in C++ anymore. All you need to do is write your code in Faust, and then Faust will automatically generate for you like quite very well optimized C++ code. And at the same time, a very important thing about Faust is that they have these Faust 2 scripts that allow you to target a whole series of target platforms. And this is just a screenshot from the Faust repo of just a small like subset of the amount of things that they support. And so with this, we started, this kind of frames like the motivation for our research, because we started to ask ourselves, like what kind of hardware do we need for a particular Faust program to achieve the performance that we want? And the second question we asked ourselves was, could the Faust programming framework point the user towards the minimal required target? And so to answer these questions, Faust actually has some benchmarking tools already. And what the benchmarking tools do is that they run the Faust program as an ELSA GTK application, and what they do is that they take a fixed number of tiny measurements, and they return to you the results of that in megabytes per second. And with that, you can find out a bit about the throughput of the program. I think a few years ago, they also they applied the benchmarking tool to the WebAssembly code as well. And this is just a screenshot I took of the results that they posted on the Faust website. And so as a runtime tool, however, there is an issue in that the results are dependent on the machine that it's run on. And as a result of this, the user has to own the hardware that they want to test out. And at the same time, having to rerun the benchmark tests over and over again can be rather time consuming. It has to be said though that I believe these benchmarking tools were initially developed to test out different compiler configurations, and so it wasn't really specifically made for testing out implementations. And so with that, we looked at what a workflow of Faust would look like using the current benchmark tools. And you see that on the right, the diagram on the right here. And so users would typically, you start by writing a Faust program. You would then compile it to a target implementation, and following which you run your benchmarking tools to check if the performance is meeting what you want. And if it doesn't meet it, you have to start again and maybe alter something in your Faust program, or maybe even in the C++ code. And from there, you go through this whole loop again, and only once you're done can you be finished. And this could be rather time consuming. And so what we proposed instead was to model the Faust program as a synchronous data flow graph, or SDF. And what this allows us to do is that it allows us to use static analysis tools and techniques that have been already made for the SDF. At the same time, these tools don't just give us data, information about the throughput of the program. It also gives us additional insights into factors like that might be influencing the performance of the Faust program. Perhaps if a certain group, certain feedback cycle might be influencing the throughput. And so the key byproduct of this is that we now divorce the performance evaluation aspect of writing a Faust program from actually running the Faust program. And so before I get into how we try to model Faust programs as SDFs, I just want to briefly introduce the SDF model of computation. So SDF is a model of computation where programs are represented as directed graphs. And so in this graph, you have nodes, which are actors that whenever they execute or fire, they consume data from their incoming buffers, and they produce data onto the outgoing buffers. And if you look at the top here, we have some numbers. Here. This indicates the number of the amount of the tokens of data that the actor would produce or consume upon its firing. At the same time, we have execution times of the actors. I just listed out arbitrary ones here. So for example, actor B would take 2 time units to execute, whereas actor D would take 3 time units to execute. And so between these actors, we also have channels, and these represent first in, first out buffers where data can flow between actors. And what they indicate to us is also data dependencies. And so with regards to like a Faust program, we could see the actors as perhaps emulating operations performed on signals, any arithmetic operations, for example. And so what the key thing about synchronous data flow model of computation is that these execution rates as well as their production and consumption rates, execution timings as well as their production and consumption rates are statically defined. And this is important because we can apply these static analysis techniques. We don't actually have to run it to find out how quickly it's gonna, the performance evaluation metrics that we want to find out. And so now that we're kind of familiar with SDFs, I'm just gonna present a basic example of the modeling process and how we approached it. Before that though, as a result of the static analysis techniques, we can find out some things about the programs that SDFs model. The first is whether or not the program will deadlock, meaning if there are any actors that are starved of data, and thus the program can't even run. And luckily for us, Faust handles most of that. In fact, Faust ensures that the graph is always live. And second thing is how frequently can actors execute. And we look at that through the property of throughput that we can compute from the SDF. And finally, we can answer the question of how long it takes for data to be processed. We call this a delay or latency. And so I'm just going to quickly move on to a simple example of how we might compute that. So typically with SDF, we try to write a schedule. And I'm just going to give a quick example of how we construct the ASAP schedule or a self-timed schedule, where actors fire as soon as the data that they need is available to them. So this is just a simple pipeline of 3 actors, requiring 1 token each. And so in the first time unit, only actor A can fire, and it takes 2 time units to fire. So at the end of 2 time units, it's going to produce 1 token of data. And I've colored this orange just so that we can keep track of this first token of data and how it flows through the graph. So in the third time unit, both A and B can fire, and B would then consume this orange token. Right? And because they take 2 time units to execute, it's only at the end of the 4th time unit that they both complete their executions. And at this point, C can finally fire. And so at the start of the 5th time unit, C will consume that token. And then at the end of that 5th time unit, C will be done, and that orange token will have passed through the graph. And so we just keep repeating this, and then we will have a nice schedule here for us. And so if you look at the orange portion here, we can see that we can see that this graph has a delay of 5 time units. And the throughput of it, if you look at this portion of the graph here, every 2 time units, each actor fires once, and so we have a throughput of about 0.5 or 1/2. And so, given this model of SDFs, we tried to model Faust programs as SDFs. And the great thing about the Faust compiler is that they generate these things called signal expressions. And so this is just a little toy example of a Faust compiler, and it's going to act as like our base case. So it just takes an input, divides it by 2, and adds 1 to the value to generate this output signal. And this is the signal expression it generates. And so I think there are 2 things to point out here, to notice. The first thing is that Faust has already done some optimization for us by replacing the division operator with the product operator. And the second thing to notice is that it really looks a lot like a SDF, like what I was showing you before. And this is important to us because this is the first thing we noticed as well. It's like, oh wow, this looks a lot like what we are studying. And so with this base case, it was we could simply do a one-to-one mapping, right, where each of the nodes will either produce a constant value, like 0.5 or 1, or they would act on the values produced by these other constant values to produce their output, such as the product or the addition operator. The only exception being the input and output nodes, and we decided to model those actors as well. But of course, you could alter the production or consumption rates to match various sampling rates. So while this is quite simple, it's not always the case. And so I'm just going to go through some the challenges that we faced and some of the workarounds we came up with. So our big issue is that the operators in the Faust signal expressions aren't always directly compatible with SDFs. And the big thing, the first issue that we faced was that of delay operators. And so this is the signal expression of a one-pole filter. And if you see the add components here, those denote delay operators. And how they function is that given the argument in blue here, for example, it would delay sending the input signal to its output by that number in samples. And this doesn't really match up with the SDF model. And so what we did to mimic this behavior is that we replaced all of the delay operators with a buffer with an initial number of samples matching the argument given to the delay operator. And this on the right here is just a simple example of what we did. So the input signal here goes into a delay operator with an argument of n, and from that it gets sent to the output signal. And so this is the pre-transform. And the post-transform, we remove the delay operator and replace that with the buffer of with n initial tokens of value 0. And another big issue we faced other than this, before that, and so given this transformation, we end up with SDF that looks like this. And the thing to point out here is that the delay operators have been removed, and in their place are initial tokens. So you can see one here. Yeah. And another big issue we faced was defining execution times, because that's really the big key thing we want to do. So in instances like in FPGAs where you can have guaranteed execution times, this is great because you can just set it to the implementation, the execution time of the implementation we have. In instances where we don't have these fixed execution times, or we don't have guaranteed execution times, what we have to do is that we have to set it to the worst case scenario, the worst case execution time, and we have that as the execution time instead. And so with this transformation, we tried to perform some basic performance analysis of one of the Faust programs, which was Echo. And so this is a bit hard to read, but this is the signal expression generated from Echo. And it might look a bit complex at first, but I've split it into two subgraphs. And the subgraph in gray, all it does is that it converts the argument given by this H slider here from, I believe, milliseconds into samples, and it feeds that into this delay operator here. And so the part we're more interested in is this red portion here. And using the transformations I described before, we generated an SDF that looked a bit like this. And so the thing to point out here is that, once again, with an n here to denote that there's a variable amount of delay that you can have. And so with this, we try to generate an ASAP schedule to compute the throughput. And if you recall, throughput is the rate at which the SDF is able to process its data. And so we constructed a self-timed schedule in the manner that we described before. We just set the sampling rate to 48 kilohertz, and then we set value of n to 3, and we left all the GUI elements to the default values. And so with that, we got this ASAP schedule here. And so based off this ASAP schedule, we found that the graph had a throughput of about 1/14. And so with that, that's the performance analysis we were performed to get. And so having said this though, there are some major limitations to our work that we need to address. And the first thing is something that I've mentioned before, and that's timing accuracy. In instances where we have to set the worst case execution time as the timings, we're going to end up with some amount of performance, some amount of overestimation in our performance analysis. The other issue is that of dynamic variables. And so you would have seen that in the example of echo from before. And our workaround initially, or rather right now, is to just compute all possible values you could send to from each variable, and then from there we compute the possible throughputs you could get. But of course, this isn't very elegant at all. And so something we're looking into is to using scenario-aware data flow graphs. And this is a multimodal version of a SDF that might be able to help us with this limitation. The next big limitation we have is that our current model purely focuses on the compute portion of the Faust program rather than the full system analysis. And we are aware that there are multiple layers of communication between the input and output that could cause quite a lot of overheads. But that's it though, it's not all like doom and gloom. On top of this work, we also have been looking at some interesting things. And something we're looking at is, and that we've noticed is that SDFs actually seem quite amenable to creating VHDL code. And so we've been working towards using this SDF model and using Flowpoco, which is a great software to generate working VHDL implementations of Faust programs. And so this is just some screenshots of what we had. So this is a noise program, and then this is the SDF model here that we produce on the right. And with Flowpoco, we implemented it in VHDL, and we currently don't have the expertise to actually have it run on a FPGA, but when we tried running some of the simulations, we've got the output that we expected with some nice noise over here. And yeah, so with that, I've come to the end of my presentation, and I'd be happy to take any questions.
Thank you very much, Jamie. So, do we have questions? Yes.
In the next kind of version of the SDF, I think so it was static SADF or something like this.
Yes, scenario.
So it would take into account all cache sort of effects, right? Because right now, so you are saying like we bound the instruction to be at worst actually this, but cache effects make it most probably actually a lot faster, so that you would get actually precise timing. So when you were talking about that, you were talking about more like those cache effects and how it could get better. So was it just like to have a bit details? I mean, I don't know.
Not exactly. So my current, I don't understand. I don't have like a lot of expertise in scenario-aware data flow graphs.
Okay.
But what we were talking about initially with the synchronous data flow graphs is that our execution, production and consumption rates, as well as the execution times, had to be static. Like you can't change them.
Yeah.
And with my understanding is that with the scenario-aware data flow graphs, because it's multimodal, you can then account for maybe different arguments from a variable, from like a dynamic variable, perhaps.
Okay.
Yeah, rather than looking at like cache effects.
Okay, so you would still have like an upper bound for how much time it takes an instruction, not taking cache into consideration to make more precise timing based on that.
Yeah.
Okay.
So will your analysis extend to what we heard before, the on-demand?
The truth is that I don't really know. Yeah, when I was watching the on-demand presentation just now, I was like, okay, we had quite a bit of engineering work to do before, but now I feel like there might be quite a bit more, and we will have to look into that, but I'm not quite sure just yet.
Maybe I have one question to go into what Raphael was saying. He was talking about the cache, etc. But even without taking into account the cache effect, the fact that writing to memory, for example, if you want to implement a FIFO between two nodes, it's super expensive.
Yeah.
Way much more expensive than the operations that we were dealing with. So in this kind of model, when they want to take into account the time of communication using FIFO, what do they do?
So the thing about this model is that the edges don't actually, so I said that they were FIFOs, but it was really quite a simplification of what the edges represent. In the actual SDF model, the edges aren't actually bounded. You actually you have to model the bounded edges by adding like a back edge. And so one application of it is that you could use the edge to like to map to a FIFO.
Mm.
And so in a sense, like the model doesn't really have an answer to how it accounts for a FIFO, and
Okay.
yeah, so it's more from
Okay, so it's abstract FIFO, and you don't have to take it into
yeah
account because they are not
yeah
really need to be implemented.
yeah reading from like external memory would though be yeah we recognize that it's gonna take up like even detail a lot of overheads, and it's quite a big headache.
Okay.
Yeah.
Any
So in practice we have the same problem. I mean, we use external memory, but we don't know.
Yeah.
We don't know how much it will cost. Depends on how the data are arranged in the cache payments format. So it's a very complicated problem in general.
So it's also a problem we discussed with Raphael. So the question of the memory is super. And for the variable delay lines, so in Faust, obviously it will be horrendly inefficient, but you can imagine to have only static delay lines. And if you want to make a variable delay line, you put a bunch of parallel static delay lines for every possible delays, from 1 to 10,000, for example. And then at the end, on the other side, you have a kind of selector. So changing the delay line is just changing in real time, so to speak, the selector of the one that you have to use. So would that help for you, or to take into account? No.
Yes, it would actually, but I think at the same time, yeah, I think it would, but I think the selector function, I'm not sure if that's going to affect our model, because that would be a variable that you can change at runtime, right? But if that's just to select the delay, then we would get the same. It would lead to the same effect as us trying to compute every single throughput. Yeah.
Okay. Any further question? Okay, no, we're in time. Okay, thank you, Jamie. So Nicolas, about category theory and Faust. Sorry? Okay. Oh yes, probably yes. Yeah, sure. Thank you.
Sorry, I got some spoilers right now.
Okay, so the next talk is Faust and Category Theory by Nicolas Cornell from the UK, from Kent University. Nicolas?
Sorry, I was trying to.
Okay.
Sorry, would I be able to have help to try and put just this on the HDMI?
Because if you...
You want to have
I'd like to look at the, yeah.
I think the extend option in duplicate.
Are you on Windows?
Yeah.
Extend this display.
I don't know this.
And now
Where
you
you
have
stop.
to.
Thank you very much.
I don't use Windows.
Okay.
Oh, no, it's done. Yeah, sorry.
But this one.
Otherwise, you can present like this. It's okay, frankly. If we all agree.
Okay, I'll go without the script that I wrote.
Okay.
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 All right. So yeah. Hi, I'm Nicolas Cornell. Thank you for having me. I'm here to talk about my paper connecting Faust to category theory, and specifically, as the subtitle says there, my paper focuses on showing that the block diagram algebra for Faust is in fact an instance of something called a traced prop, which is rather colloquial category theory language for a traced products and permutation category. So I thought I'd start off with a summary of the results. First of all, we've got the main thing. The block diagram algebra is in fact a traced product and permutation category. Oh wait, sorry, so if I spend some time, I do need that script. Sorry.
I think you can move it to. No.
If I take another. No, it's not coming off for me.
You can click on the top of the frame rather than the tab.
Okay, yeah, I think, sorry, I messed up earlier on trying to separate these. Is that? There we go. Yeah. Okay. Sorry. All right. I'll start again from there. So I'll start from this result summary. So the my main result is that the block diagram algebra of Faust is part of this general mathematical construct called a traced product and permutation category. Specifically for Faust, this is where the objects are signals and the morphisms are relations on signals. Apologies if this is a bit of jargon. I'm going to later on in this presentation, I'm going to explain more of what all of the jargon means. Furthermore, I think that one of my main contributions to the Faust literature is this direct connection between Faust's existing mathematical model, the block diagram algebra, and the literature available on category theory. And secondly, my other main contribution in this paper is a proof of the theorem that in the set or in the traced prop of signals and signal relations, the image of the set of delayed reactive functions under the trace is fully contained within the set of all reactive functions. And essentially what that means later on is that the one sample delay that we find in the definition of Faust recursion operator is necessary for allowing the equations to have answers to them, and it keeps the properties of the reactive functions that are signals. Apologies. What is it? So I was talking about the one sample delay. One of the reasons why I started looking into this and trying to apply category theory to Faust is because I wanted to know exactly why there was a one sample delay in the definition of the recursion, because it's a little bit odd. It's one of the most complicated out of all of the definitions of diagram composition operators. And it seems to almost be a little sort of ad hoc. But I promise you there's some very nice mathematics later on that shows how it's completely necessary. And then I found that in order to answer the question about why the delay is there, I also need to develop some concrete reasoning about why each of the other diagram composition operators, when you give them signal processes, the reasoning for why they always return a valid Faust signal processor. I needed to find out mathematical reasoning for that. Okay. I'm now going to give a little bit of an explanation on what a traced monoidal category is in terms of computer programs. So at the most basic level, a category is just a mathematical abstraction of a system that has objects, morphisms that map between those objects, and a method for defining sequential composition of these morphisms. And then what category theory rather allows you to do is introduce more structure onto your category. So here we've got traced and monoidal as adjectives in front of category, and those allow you to model with mathematics this new sort of very interesting type of behavior. So if we look at this little table here, to try and give a sort of a concrete explanation of what a category is. So with the objects, with a computer program, you might think of data types. That might be integers and strings. Then the morphisms, or just the programs and functions and processes that map between these data types, and that would essentially be something like a function that returns the length of the string, mapping from strings to integers. Morphism composition is quite simply just sort of sequential composition of functions. And then the monoidal product of morphisms would be parallel composition. So this might happen when you have multiple processes and you can run multiple programs at once on those. Then we also have the monoidal product is special in a way that it acts on both morphisms and objects. Because if you think about trying to define what the input is for a parallel for two programs being computed in parallel. You're trying to add together both of their inputs and add together both of their outputs. So that's why the monoidal product acts on the objects, and that would give you an idea of sort of a tuple of data types. And then the trace is simply just a way of modeling recursion or feedback in the category. Sorry. Okay, so now that's all sort of very abstract mathematical concepts, but I wanted to give a little bit more of an explanation of why you would use specifically a monoidal category to model Faust's diagram algebra. So as you probably already know, Faust has its own block diagrams, which the block diagram algebra is models of an abstract mathematical model. And here where I've put a lemon meringue pie recipe, is a mathematical model called string diagrams that comes straight out of monoidal categories. Because as we said earlier, you've got two ways of combining functions. You can do it in parallel or in sequence, and this can be sort of thought of as the two dimensions of combining things. So here, if you've got the make lemon filling and make meringue, those two can happen in parallel, but the separate egg yolk has to happen before those, and so it's combined in sequence in that area. And so in this way, even the arrangement of all of the elements of the diagrams encodes information, such as I was saying earlier, if things are arranged vertically, then they're being computed in parallel, and if they have the strings connecting them, they're being composed in sequence. And the same is true for block diagrams. Alright, so here I've finally got some nice mathematics for you guys to look at. This is just a set of definitions before we go further on and more complex equations come up. So on the top left we have the glue operator. This is a stand-in for monoidal product, and more or less just as the monoidal product on objects. Lets you combine those in parallel. And in my definition, you put the left variable under the right variable when you draw them as a diagram. The next is, below that is the slice operator. This allows you to choose, this is just there to choose or select or ignore certain signals. And then you have the restrict operator, which takes a signal and a time step as input, and returns the values of the signal from time step 0 up to the input time step. And this particular, well, it's a morphism within the category, because it acts on signals and outputs a signal. This particular one is going to become very important later on, because it's part of my definition of a signal processor. And yeah, and so yeah, here with reactive functions, as I'm sure you probably already know, a function is a map between objects that has a it has for every input it has a defined output, and that output is unique for each input. And then lastly, a definition of product and permutation category. So I've been switching around with monoidal category and product and permutation category. So here it's just that product and permutation category is just a strict symmetric monoidal category, and I'll explain what strict and symmetric mean very soon. And furthermore, there needs to be a bijection in this prop between the category's objects and the positive integers in my case including 0. Alright. So now I'm going to describe the features of the underlying category that's going to be used in the model for the block diagram algebra. I won't dive deep into the proofs of why these features constitute a block diagram, of why these features constitute a category, but I'll give you an idea of whether any of them had an interesting past to it, or whether the setup of this category actually made it easier to prove some of these things. So the objects of the category are going to be sets of signal tuples of a specific size, and sorry, I've gone too far. There we go. Yeah. So the objects are positive whole numbers, sets of signal tuples, and these can be related to the positive whole numbers. You either have the empty tuple, which would relate to 0, or any pair of signals would relate to the positive whole number 2. And I did this because the contents of the signals don't matter so much as the number of signals that are present. Furthermore, I chose to model the signal relations as reactive functions, as I said earlier, because they have a unique output for every input, and because they passively receive data and process it immediately, and so that links into the reactive part. You can define a sort of a partial pardon me, that wasn't the point. Sorry, I'll move on from that. Okay, and so, but in this category, I've chosen to model the or set the morphisms as, instead of reactive functions, relations on signals. Now, relations are just a more abstract version of a function, and so reactive functions are included within that definition. And I used relations on signals just because it made some of the proofs later on a little bit easier. I'm now going to describe the monoidal structure, where the monoidal product is the mathematical analog of parallel composition of signal processes. So as you can see here, the monoidal product operates on objects as being defined by addition. This is just because when you combine signal tuples, you just get a larger signal tuple by adding together their sizes. And on morphisms, it's interpreted as graphically as stacking the variables on top of one another. And algebraically, it allowed together the sizes of the signal tuples, and the composite morphism will have the combined actions of the original two. Next, the definition of a monoidal structure requires an identity object. This is just going to be the set containing the empty tuple, or 0. And this object is special because obviously if you add no signal tuples to 7 signal tuples, you stay with 7 signal tuples. Hence it's named the identity object. And furthermore, this is where the setup of the category makes it much easier to define the monoidal structure. Is that we can define the apologies, you might not be able to see this diagram over here quite so easily, but the associator and the left and right uniters can be defined as identity natural isomorphisms, and all that sort of like adds up to mean is that when you're taking the monoidal product of objects, it doesn't actually matter how you order the brackets, because this is because the monoidal product is defined by addition, which itself is associative. So actually this thing here is called the Pentagon Diagram, and essentially it just kind of collapses into a bunch of identities in the same object. A similar thing happens over there on the left with the triangle diagram, which dictates how the left and right uniters are meant to act. And so the left and right uniters are the category's internal definition of how the monoidal product acts with with the identity object, and so yeah. Okay. Finally, we get to the symmetry. The symmetry essentially allows, graphically, it can be interpreted as allowing wires to sort of cross over each other and swap them. So the symmetry falls under quite a few rules and conditions, because it has to its interactions with the monoidal product, with the sequential composition, and the associators and left and right uniters need to be defined and dealt with. But luckily, this is where another one of the simplifications comes in. So the top diagram is the original associativity coherence with the symmetry, in that one, because the associator is an identity natural isomorphism, this means that all of these things that say A, ABC, BCA essentially become identities themselves. And so that collapses the associativity coherence diagram into the triangle that you see at the bottom. And there I've swapped out the monoidal product with the symbol for addition, because that's how it's defined on the objects of the category. And furthermore, the symmetry also needs to be a bijection, and it's also needs an inverse, and that's just the sort of algebraic way of saying that when if you've crossed over two wires, you can uncross them. So in some senses, quite a lot of the rules on all of these parts of the categories seem to essentially be sort of a common sense. Yes. Sorry, this is where I've lost some slides, but here, if I'm able to use the whiteboard, I can draw some pretty pictures and talk about how the how we can now that we've defined the category, we can talk about how the monoidal product and sequential composition preserve reactive functions. So that's yeah. So it's important that we find out whether these whether the monoidal product and sequential composition preserve reactive functions, because that's our abstract mathematical definition for what a signal processor is. There's a red
Oh,
box
yes,
on there.
sure.
Yeah. Okay, so in order to prove that the monoidal product and the sequential composition preserve reactive functions, you need to show three things. The first is that for any input there is an output. The second is that for each output that you've defined, it also needs to be unique, and that constitutes just the definition of a function. And if either of these two were broken, then we wouldn't have a reactive function, and we'd be able to say that these diagram composition operations weren't able to preserve signals. And then so the third diagram. The third requirement is that the function is also reactive. so for sequential composition, because we're working with relations and deep within something called the category rel of just relations on sets, so the category of relations on signals forms something called a subcategory, and that allows us to take for free that the sequential composition preserves functions when it's given functions, and you can also sort of see this for yourself if you think that if you already have two functions that are reactive and you put them together with a in sequence, then there'll always only be one output. The output will be unique, and if your initial morphisms were reactive, they will stay reactive. Yeah. So the next thing would be to show that the monoidal product itself has also preserves functionality and reactivity, and once again this is sort of quite obvious to see because the when you're composing two signal processes or reactive functions in parallel, you aren't doing anything to change whether or not there is an output, you aren't doing anything to change how many outputs come out, and you aren't doing anything to change
You are a little short of time. Can you conclude in 5 minutes? Is it
yeah.
okay? Sorry for that.
So, yeah. Okay, sorry, I'll move on to trace. Okay, yeah, so I guess one of the most interesting things about this category is the fact that it has a trace and this can model recursion. So on the board over here, I've got the signal, the string diagram version of what happens when you take the trace of a function, you just plug an output into an input, and as you can see up here, they need to be of the same size of signal tuples, and this output function is defined in the line of logic above. So this is defined using notation for relations. So A in this case would be the input and B is the output. So we say that the input-output pair AB is in the trace of the function if and only if there is a variable in the trace line such that in your original function you have that the sort of A glued to X and B glued to X exists in F. So in a sense, you can view the trace as being as taking away information from the original function. So the here I've highlighted these coherence conditions for the trace. which are called naturality and tightening. As you can see, this is just sort of the common sense for how you'd want the trace to work. You've got on the top diagram, you can essentially slide any function on the trace line. It can be on the output, on the input, and when you take the trace, you should still get the same function returned. And then on the lower diagram, you have that if you have naturality in the untraced line. So the lower diagram is called tightening, but that's just another name for naturality in the lower line. And so this essentially, as you can see here, if you take the trace of f combined with h and k, that's the same as adding in h and k after taking the trace on f. And here we've got the final three coherence conditions. So we find through yanking how the trace interacts with the symmetry. As you'd expect, if you trace the symmetry, you should get back like a very convoluted identity. With superposing, you get that if you take the trace of your function tensored with the identity object, then that's the same as tensoring your traced function with an identity object. And then down the bottom, you have exchange. And this is a rule for saying saying that it doesn't matter, in a sense, which order you trace the lines in. As long as you trace the same number of lines in the same lines, you should always get the same output. And so these 5 coherence conditions, yanking, exchange, superposing, naturality and tightening are all sort of the next best thing to common sense rules for having a trace in your category. And they all partially deal with the trace interacting with a different part of the category. So as I said, yanking was the symmetry, superposing is with the tensor product and identities, and exchanges with different orders of taking taking the trace. Okay, so now we've defined a trace, and we've also gone through and I didn't show this, but all 4 of the other diagram composition operations do preserve the properties that I've listed up here. So they both give, all of them give something with an output that exists for every input, for every output is unique, and the function itself is reactive. So here, as it says, the trace by itself doesn't actually preserve functionality, and the way to think about this is that once you trace this thing, which I've called copy, so it just takes in an input and produces a duplicate of it. So once you take the trace, you then have no inputs on one side, so that means you can view it as a map from the empty tuple. And this makes it easier to check whether the output for every single input is unique or not. And on the last 2 lines, that's the logic for seeing that in the trace condition. So yeah, the main takeaway is that the trace doesn't actually preserve functionality. but not all is lost, because we can preserve it using the one sample delay. So the way to go about transforming your function that you want to trace and you want to keep it as a signal processor is that you combine it with a delay along the lines that you want to trace, and then you take the trace of that line, and down here on the bottom is the algebraic representation of the recursion operator, and yeah, that's
So the triangle X is the delay operator?
yes. Yeah, the delta is the delay operator, and the identity is the identity. Are there any questions that people would like answered? I'll try and answer very quickly.
Are there any questions? We are really running out of time. I'm very sorry for that, because it's super interesting. It's most interesting to see this kind of connection. But we are very tight for the time, because there is the opening of SMC. We need to transport the equipment, etc. So I suggest that the question will be postponed for the coffee break. So we can discuss, you can ask Nicolas any question during the coffee break. Unless there is a super urgent and very short question. Okay, so we move to the next presentation, and thank you, Nicolas. So the next presentation is going to be done by Stéphane, and since we are late of 17 minutes, we will have to make a short coffee break. Thank you. C'est 15.
So my talk is more concrete. Sorry for that. Basically, I'm going to talk about what has been developed into the Faust ecosystem and community since last edition of IFC. You can get the PDF if you need to on GitHub repository. And since we are three authors, Jan and myself we are working at RAM, and Romain Michon is now working in RIA. The agenda, there are some new things into the compiler, new backend, new option, internal API access, new architecture file. We have done several things to help developers debug, optimize, deploy their code. New libraries, some are now part of the standard libraries and some are external contribution. Documentation, workshop, tutorial, and how we try to animate the community, and some perspective. We had two different backend contributed. C# backend contributed by Michael Iffen, and basically he wants to use C# as a target language because he wanted to do dynamic compilation using the .NET compilation chain. I don't know exactly if it's already working, but it was his project at least. There is a new backend to output a D-Lang language, contributed by Ethan Recker, and In this case, the idea was to be able to use an audio plugin framework called Debug, which is also actually developed by a French guy, Guillaume Piola, I think, in Grenoble. And last, at Gram, we developed last year Julia backend. So the idea was to have a look at Julia language, which is quite an interesting new language, used mainly in data science and scientific computing, and we want to try to see if we can do some kind of machine learning by connecting this kind of environment and Julia and Faust, and so the idea was to be able to generate Julia code directly and see what we can do, maybe at signal level. We have new option into the compiler. The main one is mem options. It was already there, but we have extended a bit the semantic and the use case of this option. Basically, in some cases, we want the DSP class generated by the Faust compiler be able to change the way the memory layout is described. Usually, we have a flat memory layout, but in some cases, in particular in embedded platform, we need to be able to allocate memory zone, memory region in several parts of the different section of the memory on the board. And in this case, we need to be able to describe this in the generated code. And the one sample option is a way to separate control and compute. The regular Faust compiler basically merge the compute, the control, so everything which is computed at each change of control value, basically at block rate. And here, with this new option, we have a way to separate with two different functions, and this allows to call the control function possibly in a separate way, and call the compute function at separate places into the architecture file. And we use this in particular in the Faust project when we want to target the FPGA. And in this case also we want to compute sample by sample. So with the OS option we can have a compute function that allows to compute only a single sample each time. We have done a work consisting in exposing internal APIs. So now there are no more internal. So the idea is to give access to developers to part of the compilation chain. Here you see part of the compilation chain, and without going into all the details, at some point we may want to let developer build in another algorithmic way trees, either what we call the box API. So basically it's the circuit. Jan was using the circuit terminology, but we also use box terminology, and the signal terminology, which is further in the compilation chain. By giving access to this API, it means we can possibly imagine projects that would use part of the compilation chain and build some new tools on top of this. The box API, so basically we have a new header to describe that. We have a tutorial to explain how you can build in C++ using the box API and generate the final executable code, for instance using C++ backend or LLVM backend. And well, we could, for instance, imagine to use something else, not directly using the block diagram algebra, or try to do some kind of machine learning at some symbolic level. Then it will help possibly to be able to create box trees by program. The Signal API, so again with a new header file, a tutorial to explain how you can use that on the Faust website. We could imagine to have pure graphical languages, graphical signal-based languages, using again the last part of the compilation chain. Could be interesting to see if it's interesting. And the idea to open also this 2 point into the compilation chain came when we saw a new language appearing, which is called Elementary. And basically it's a functional language for DSP audio, but basically their model is the idea of describing a signal graph and having a JavaScript language as a language to give you the ability to compute, to describe the graph basically. But so it means we could do that, this kind of separation between the language to build the signal graph and the signal graph itself. New architecture, we have developed a Faust to VCV rack architecture that allows basically to process any DSP, Faust DSP, and produce this nice orange graphical user interface, which is not yet very nice, as you can see, but basically it's VCV rack was demonstrated by Raphael this morning, so it's a modular synthesis model going purely in software, and you can, as a developer, you can describe new modules using C++, or in this case Faust, and you can possibly generate automatically the graphical user interface, but in this case it's still a bit of work to make it look nice. We also have a new DAISY architecture, so a Faust to DAISY tool. Again here the idea is to target a new embedded board and having an automatic way to translate any DSP, Faust DSP, and to target the DAISY. So DAISY can have different form, only the chip, but also a pod with 2 buttons or 4 buttons, or they have these different ways to integrate the chip itself. And as you have seen this morning with the Aurora block project, there is also this new way of using the DAISY and this new way of using Faust to automatically, in this case, generate the module itself. Debugging, well, even if Faust is supposed to be a language when you cannot produce incorrect code, the thing is that right now the interval computation done on signal is still not correct in all cases. So in some cases you can write programs that will possibly read and write outside of tables because since we don't have a perfect interval computation, we more or less deactivate it at some point into the compiler, so we may have incorrect expression, signal expression computed. So with this expression, with this CT and CAT option, you can possibly check part of this read-write operation and be sure that the code will not crash at runtime. So this is, well, obviously it's not satisfactory to have to do that, but it's a concrete way to let the developer check his code, and we hope obviously when the interval computation will be more correct not to have this option anymore. We have also a math exception option which aims to check if we are using math function into their correct domain of operation, like taking square root of positive number and this kind of thing, and we can check that part at the compilation time and part at runtime. Otherwise, you can possibly have code that produce not a number or infinite value, which is obviously not what you want. And we also extending improve the intertracer tool that was presented 2 years ago. So we have an interpreter backend into the Faust compiler, and this backend allows to generate bytecodes that we can execute into a kind of virtual machine, and we can instrument this bytecode and check a lot of things into this virtual machine, and we can check that we are not accessing memory outside of the tables, and check domain of mathematical function, all this kind of thing. And then you can have a trace, which is quite useful because you have a trace of the bytecode that you are executing into the virtual machine. And we have extended all this into a more complete documentation. Optimizing, we have already presented this idea of using tools to explore the set of compilation options that you can give to Faust for a given DSP. So we have two tools to do that, FaustBench and FaustBench LLVM. FaustBench LLVM use the LLVM backend to generate different shape of the code, the scalar code, vectorized code, and with different values for compilation option. And using that, you at the end of this process, you know the best set of compilation option you have to give to the Faust compiler for given DSP. And then you can use the same option when you compile the C++ version. We also have developed a new Faust 2 object tool, and in this case, the idea is to allow developer to target, to create a multi-CPU C++, compile the same C++ code for a multiple set of CPU. Since especially when you are using auto-vectorization, when you target exactly the CPU when you are going to run, you can have quite better performances. And this tool is not really a Faust tool, but well, it's helping developer to better optimize the C++ code used by the Faust compiler. And in particular, we did this work to help Expressive-E. Expressive-E is a French company doing different things, but in particular they are developing a new synthesizer called Noisy, and the DSP part of Noisy is completely written, or almost completely written in Faust. And we helped them first to find out the best compilation option using the Faust LLVM, FaustBench LLVM tool, and then later on using the Faust 2 object tool, they can be sure to have the best possible result. And we have also documentation for that. New libraries that have been contributed by Dario, who was there this morning, but I think he's not there anymore. A library to do anti-aliasing kind of computation. And we have two new libraries into a physical model domain. One contributed by Ricardo Russo, he did that at RAM, to do finite difference scheme physical models, and another one contributed by Dirk Rosenburg to do a wave digital filter kind of physical model. And I guess he was also working with Jatin to compare this Faust library to Jatin very fast templated based C++ code. And I think sometimes Faust wins, sometimes C++ templated code wins. You can discuss that with Jatin later on. Several contributions from the community. The abc.lib library, which was presented by this morning, done by at Paris 8 for mix and music, basically. Dario also contributed two libraries. Edge of Chaos is a result of his work done during each PhD, basically describing music complex adaptive system using Faust. Another real Faust library to deal with imprecise or domain-limited version of malfunction, to be sure you don't compute code that could be outside of their domain and produce not a number and infinite results. And bit DSP Faust, which I think was already described at last IFC, but now it's community contribution, and another contribution by Italian composer. And also this library is developed, continuously developed. We have worked a lot of documentation. We even receive a prize for that open source prize. We have the French research comment on dit, département de la Ministère of Research France did there were several prizes for several open source well-known open source projects in the French community of academic community, and Faust was had a prize for quality of his documentation. And in particular, we did a lot of documentation, and especially the architecture files, which is something that you have to understand when you want to contribute a new architecture. And and we did some workshop during COVID time. So, especially, I think Romain organized a workshop on physical model with 4 presentation. Dirk presented his web digital model library. Ricardo was presenting his work in infinite difference scheme, and we had also another presentation about, on mass interaction kind of physical model. We have several new tutorials about the community. So the idea is to try to animate the community. So I am on the Faust Slack night and day. And we also have a Faust channel on the Audio Programmer Community Discord, which is a well-known community animated by Joshua Hodge and a lot of audio developers, from beginners to professional level audio developer are on this community, so it's quite interesting to be there. And this year we have 2 Google Summer of Code projects that have been accepted, and we'll have a project to integrate Faust in ICE environment, and another one to integrate Faust in Bespoke, which is another environment. And we have the Powered by Faust page. So basically the idea here is to list every possible significant Faust project we can find and put some word, and so that you can have a look of the variety of projects that are now using Faust in different ways. Sometimes it's purely a complete project in Faust, like a plugin. Sometimes it's using DSP done in Faust, and we have also Faust integrated into already existing environment. Musical, artistic project, some projects which are a bit outside of the audio domain, like maybe this one, analyzing biosignals using embedded platform and using Faust as a language to describe the DSP. You can have a look, and even if those projects are, for some of them not actuated anymore, you can still in some cases find or get some working DSP, Faust DSPs that you can possibly reuse in other projects. Perspective, so Jan is going to analyze the Faust survey we did this year to have a kind of feedback of the community on what we could improve into Faust language and ecosystem and everything. We maintain a Faust ID page that you can possibly look at. On this page, we did a presentation of several IDs that could be Google Summer of Code project, but we also maintain a list of things that we never have time to complete, like trigonometric simplification, proposal by Pierre Leconte, but well, this is an old proposition, but well, the idea for instance would be to extend the language to be able to do some kind of simplification into the compiler itself to improve some kind of use case like Ambisoni DSP. Well, and maybe you have your own ideas. And this is the end of my talk. Thank you.
Thank you, Stefan. So, the problem is that we have 9 minutes left for the coffee break
Yes.
and
So
the
we
questions. So, do we have some very quick questions for Stefan? Or same that for Nicolas, we postpone to the coffee break?
For shortening the coffee break by quite a bit.
Okay, voilà, on va faire comme ça. Okay, so let's go to the coffee break, and we start in 7 minutes. So, yeah. think we should start. If it's okay for you. Okay. So we have a round table and we should discuss several topics, and I will start with the result of the Faust survey we did recently. So we had 71 answers, which was not that much, but at least it gave us some results. So the first question was, is Faust your main or secondary computer music language? So the answer are 50-50.
Yeah, there is nothing on the screen.
Nothing on the screen, okay.
Ah non, il faut brancher l'autre câble.
Branchez votre câble.
Non, c'est plus le splitter maintenant, c'est HDMI.
Celui-là?
Ouais, c'est ça.
Okay.
Tu peux
That's
débrancher.
the reason why. Okay, so we the second question was, what other computer music languages are you using? So we see that the maximum number of answers were for Max, then Pure Data, so but then also Super Collider. I was surprised that C Sound was not that much, and Gen not that much too. So these are interesting results. Chuck a little bit, and yes, essentially these languages. So what is your Faust programming level? Well, nearly 60% of the people says that they are average, 8%, well, nearly 9% experts, and 34% beginners. Well, obviously it's not very easy to answer this kind of question, because what are you saying, that you are an expert? This was an interesting question. Would you say that Faust programming is rather easy or rather difficult? And nearly 60%, 6 people to 10, think that it's rather easy. Well, I think that Faust is basically easy, but not everybody is convinced of that, but okay, we have to work on that. But that's encouraging, I would say. What is your programming language background? So most of the people are coming from the C++ world, which was quite a surprise. A little bit of functional programming, but other musical programming languages also, obviously. So I was surprised to see that so many people coming from C, C++. These are the people that think that Faust is difficult. This also is interesting. For what purposes do you mainly use Faust? And so a lot of people, 83% of the people, are using Faust for their own benefit, personal use. But nearly 44% of people are using it for professional development, which is quite nice, I would say, and nearly 30% for teaching. What type of application do you use Faust for? Well, I'm not sure that the question was very well. The items were a lot of overlap between the items, but most people say audio processing and effects, audio synthesis, and digital signal processing. So what's the difference? I don't know who wrote that question. Is it you, Stefan, or is it me? Okay, so it's, sorry for the stupid question. Yeah, but the level of detail was a little bit stupid, I would say, but okay. So, what's your favorite tool in the Faust ecosystem? 61% is the Faust IDE. So, Xiong, if you are listening to us, thank you again for providing the Faust IDE. And Faust Live is not used very much. Faust Playground, not so much. And the command line. So obviously most people are using either the Faust IDE and the command line or vice versa. When we ask what other tools of the Faust ecosystem are you using, so most of the people say the command line. So maybe we should stop maintaining Faust Live and this kind of, no, I don't know. On which platform do you mainly develop? That's interesting for us because we know that, for example, we don't support Windows very well, and most of the people are on macOS and Linux. But that may be because we don't support the Windows very well, that people are not coming and using Faust on Windows. And web platform, yeah, maybe, I don't know, maybe it was not a good item to propose a web platform because, well, the intention was, do you develop for the web platform per se, and not a lot of people. Okay, so for which platform do you mainly develop? macOS and Linux, and embedded systems. So nearly 40% of people are developing for embedded system, which is quite nice. And FPGA, well, we hope that in 2 years the number of people using FPGAs will increase. Android, more Android than iOS. Web and Windows, yes, still people, part of people developing for Windows. So what are your favorite plugin architectures? So by far VST. I thought it would be more balanced, but no, it's clearly VSTs. Well, obviously VSTs works everywhere, so it's and then Max externals, LLV2, which is quite nice, audio units, and Super Collider UGENS, pure data. But obviously, probably, yeah, means that if we need to put efforts, we should put efforts also on the VSTs. What's your favorite cross-platform GUI toolkit? So Juice, by far the nearly 60%. Qt, 28%. GTK, FLTK, MIGUI, not that much. VX widgets, not. And others, but okay, I don't know what are the others. Which is nearly 24%, the people saying others, so what could that be? I don't know. No, that's the conclusion. Most of the questions were, well, it's not easy to do, and probably well, next time we can have better questions, and hopefully. Have you ever contributed to any of the following areas? So bug reports. So probably 52% of the people contributed to bug reports. Well, which is nice, but contributing to bug fixes would be even better. It means that also we still have bugs. Answering to users' questions, 50%, which is super nice. because I think that people appreciate the fact that obviously Stefan never sleeps, so he always answers, but others from Dario answer a lot of questions also, and that's super useful, I guess, for people starting with Faust. So, answer to question, architecture files, really? 29% contributed to architecture files? I'm surprised. Maybe bug reports in architecture files, or Faust examples, libraries. That's true. Well, for me, I was expecting people contributed more for libraries than architecture files, so I'm surprised by the result. But anyway, so we can say that even if the community is not super large, it's very active and very responsive and very helpful, I guess, for people coming to Faust. In your opinion, what are the strong points of Faust? Okay, so efficiency of code was the first item, 70%. Variety of supported targets, 65%. Expressivity of the language, 55%. Online tools, 55%. And community support, nearly 50%. Well, I think it's fair. What do you like to see improved? Sorry. Well, I did not understood completely all the answer. Making coupling of GUI, MIDI, poly optional. It's completely optional, but okay. Okay, so fixed point code generation would be also interesting. Syllab backend would be nice. Okay. More example and project, FFT convolution, yes, okay, sure. Frequency domain signal processing, same answer. Optimization for embedded use cases, probably related to the discussion we had on memory layouts and this kind of stuff, so, yeah. Documentation. It is sometimes too abstract and it lacks intermediate level code examples. So does that mean that there are simple examples or very complex examples, but not intermediate level? Probably.
Yeah.
You agree with that? You wrote that.
Yeah.
Okay.
No, I didn't.
Yes. So.
There are very simple examples, and then you have library calls. You don't have extended.
Okay. Okay. Probably. Yeah. Sure. You're right. A way to upsample and downsample portion of the code for function like upsample, some function. Well, this is what we hope to be able to introduce with the on-demand technology. Multi-rate and fixed point, please. Okay, so multi-rate and fixed point also something that we are working on within the FAST and project and Emerald. Faust as a whole is very stable and seems feature complete to me, to my use case, but that said, I would love to see the Faust library be expanded upon even further. They are a treasure trove, but I would love to see more in there. There is one of the most important areas to me as a user because they enable complex things to be made in a jiffy. What does that mean, jiffy?
Very fast.
Okay, very fast. Yes, sure. An online forum would be great. Something like supercollidersynth.org and preferable to Slack. It's hard to keep up with the chat and a lot of valuable information is sort of locked away and disappears in there. Would be nice to have publicly searchable to have publicly searchable in a forum. So any opinion on that? So what kind of forum infrastructure we could use?
There's always Reddit.
Yeah? Yes. So that's your suggestion.
Yeah.
Mm. Oh, okay. Error messages are quite minimalistic and sometimes esoteric. Or this is very polite because he says sometimes, while quite often they are very long and yeah, it's super difficult. Frankly, it's something very difficult because we are many errors are detected after the evaluation of the block diagram, blah blah blah. It's difficult to trace back to the origin of the problem. So I don't know what to do with that.
I think that what could help with this is a little bit of formatting the errors.
Uh-huh.
Sometimes
You think you could just improve a little bit just by formatting better the... Okay, so yeah, we'll...
Reducing the size of expression, for instance.
like expression A is this, expression B is this. Maybe a little bit of formatting, it would be clear what the A and B are. Because sometimes you have to go and look for the A.
Someone once told me it would be nice to have the block diagram even if you have an error. So to see where the error is, which is probably a good idea, but not that easy to do. But yeah, there is room for improvement here. Okay, I'm still learning Faust. I do not I love desktop version of the Faust IDE as well as the ability to make custom GUI with my own style. Well, custom GUI is using Juice, for example. And a desktop version of the Faust IDE you can install because it's how it's called progressive web app, so you can install the Faust website as an application. Borrow some constructs from hardware design languages and support recursion with a notation that has the exact same mathematical power of tilde, but in a way more intuitive for engineers and musicians. Well, you have that a little bit with the how it's called again, the Letrec, yeah, with the Letrec construction.
If you have a question, ask Dario.
Okay, yeah, sure. Dario, please come. Unbundle the lips, install cache for the tools, so there is no duplication or inconsistencies. What does that mean? Because the libraries are a separate project, so that was the point of doing that. I'm not sure of that to understand fully. Versioning link to Git in the web editor. Yeah, there are obviously many extensions we can imagine in the Faust IDE of being able to support or open a Git repo or doing this kind of stuff. Faust, the IDE is a great prototyping tool, but still look like a prototype itself. Yeah, okay. Yeah. That's not fault, but even well, it has a lot of super interesting features at the same time. So it's a little bit severe, I would say, as a comment. Okay, so Leslie, the device. Maybe I should not read everything. Usability, feedback, testing. I don't know how I can share this, the results.
You can export the PDF, maybe? You mean you want to export the...
Yeah, well, I will try to figure out how to do that so that you can look at all the answers on the Faust website. Better memory management for embedded platforms and multi-rate processing. Okay, sure. Online debugging tools. A probing mechanism will be great. Yeah, that's sure. Yes, Being able to use the phone as a visual ID would be great, especially for so that would be mean to have a Max-like version. What does that mean? Use the playground. Okay, the Faust playground. Okay, yes. For example, in the Faust playground, you can edit your Faust code, but not with all the fancy feature of the Faust ID. So it's probably a good idea to open maybe in the Faust ID the code or doing some link together with the two environments. I think having more intermediate tutorial. So it's like what we said before, to have more intermediate. So that's interesting. We lack of intermediate level examples and tutorials. Integrate with Juice VST creation. My biggest issue for the moment is that the view meter is considered by my DAW as an automation control, so anything to make the view meter change makes my DAW think that, okay, well, I don't, a flawless magic ecosystem would be too different, okay? Better embedded than memory addressing, this is Raphael that wrote that. No, okay. First class support for vectorized operation defined over multiple samples like spectral processing, FFT, convolution, etc. I know there's a lot of history looking into this word. Yeah. Well, I hope that the upsampling, downsampling, and interleave features would be useful for that. We'll see. Did not succeed in installing a working standalone Faust IDE on Linux Mint. That's strange. IDE, a solid patching and editing environment would be great. So she included the IDE, did also a patching environment that generate Faust code. So at some point you can imagine that the two could be merged. Obviously what would be ideal is that you type your code and you generate the block diagram in real time, and then you edit the block diagram and you regenerate the Faust code. But it's super difficult to do well. Okay, guys, I'm maybe not going to read all this because time is flying. FFT support, FFT, yeah, but clearly we knew that. What is your overall opinion on Faust? Very good, but it tries to solve too many problems. Is it true? Yeah? Okay. I'm not sure that I agree with that, but well, okay, it's an interesting comment. Okay, essential tool that hope to learn. I'm really impressed. Amazing API. Faust is very powerful language. Great, awesome. So at night when you are tired and depressed, you can read that, and it's good. Well, I think that we should take the time to analyze more deeply all the bad and the good, and
you should have paid someone to criticize, to say it's bad, just to balance it.
Well, but there are some outstanding, amazing. Without Faust, I could never be started making plugins. Community is fantastic. Well, that's we all do all the work that we do for that, to helping people that without real programming background to write their own plugins, for example. It's a great language. I wish it has a bigger community. Yeah, sure, we should improve that. Very good. Okay. So I will publish that. Very good. I would love to see a clean reimplementation of its strong feature in a proper functional language like Haskell thought. Well, there are people that try to implement the the block diagram algebra in Haskell had it was not that easy because of typing issues and yeah. I like it very much, but it lacks FFT support and can use it for many of my projects. Yeah. Okay. So okay, it was a quick survey of the survey, and we need to analyze. We will put everything online, and we will analyze more deeply the pros and cons of Faust. But okay, community is fantastic, and what else? And yes, okay, great tool. Okay, so are there any comments or questions? Well, you agree? Okay, excellent. Maybe you wrote some of this, probably. So what's the other points we should discuss? The idea of doing a kind of foundation or association, and the roundtable on the future of Faust as a language. Okay, so we're small subjects like this. So the idea of yeah, we are looking at a way to create a kind of non-profit organization for Faust that would be able to guide the evolution of the language, to have all the community more formally involved into the evolution of the language, and maybe that could be used as a committee for IFC, for the next editions of IFC. So it would be interesting to think what you think of. Imagine that there is such an association. Would you like to be part of it? How much would you pay for that? And what? Yeah. No, nobody. From yes. So is this? Do you think it's an interesting idea?
Like
Yes.
this session would be used to teach Faust, for example, or
Sorry.
the association would be used to teach Faust, to promote Faust.
Promote Faust, maybe also give directions, and having the people interested in Faust being involved and somehow, yeah.
Yeah, I think you should discuss the way the association would function, would work. I mean, the WFC used to be a member organization where you could have big members that pay a lot, and but don't have more normally in theory not more power than the small members.
Mm-hmm.
And decisions were taken using not consensus, but everyone should agree.
Okay.
So that was also something complicated.
Mm.
But now you've got big members that give a lot of money and decide that sometimes they will just vote no.
Mm.
Block things when it's not in their own interest. So what I mean is that who is going to decide what, and will the members have to vote for something, or just for supporting Faust and the core team will still continue? What do you expect?
I expect people to have the possibility to vote for something. Otherwise, well, obviously, as soon as you start to have this kind of system, it means that the evolution of the language escapes the inventor of the language, so to speak. But that's the price to pay, I would say. So it's okay for me. Stefan, I don't know, but.
Yeah, because what could be interesting is that if you have financial support from INRIA, universities, Open University, I don't know, everywhere where they are teaching Faust, for example, University Saint-Étienne, Jean Monnet, and so, because these are the members that could give more money than individuals, for sure. Or private.
But you think that the University of Saint-Étienne could ever give money, or?
I don't know. I don't know, but for example, my university is giving 8,000 euros a year
Ah,
to be a member of W3C.
do you think they would be member of
Just
the
for-
Faust association?
I don't know.
Okay. Well, in some way, we have to think about the future of Faust. What's going to happen in the, I won't say next century, obviously, but in the next 10, or when we will be completely retired and gaga and useless, and so. It's important to the language to survive somehow. So we are also discussing with INRIA, because they have foundations that could help, and
how we try to solve all the problems that have been described. We need more people engaged into the community, and each time we discuss that, we see that it's difficult to have people because everybody inside making small projects.
Focus.
more focus.
Maybe you can find listen. I don't know you say English.
Mécène, ici, je sais pas.
Donators.
Donators.
That would avoid paying some taxes if there's an association.
Actually, maybe we are mixing two problems actually. The first one is to have an association independent of Graham or me or whatever, who is responsible for the development of Faust. And the second one is, do we need financial support for this association? Today we don't really need that. I think we should concentrate on the association, try to organize it the way Faust user want it, and then when it comes that we are missing engineer or whatever, then we think to the second problem.
Yeah, sure. We should separate the two, maybe. Yeah. So Dario, what do you think? We should make an association, or?
I mean, I would love to be part of the association, but I was thinking what you were saying, the future of Faust. Like you need people who have the kind of expertise that you have. There's not many of them around, I think. So it's like the association should be used to train some people so that they learn.
Okay. Yes. Okay, yeah, it should be probably, yes, right in the status of the association, the fact to teach and promote Faust
But to have the system survive, we need to make the compiler survive. I guess this is an important point of having the knowledge of being able to understand what the compiler does and how at some point someone wants to re-implement everything. Right now it's difficult because probably it's the source code is not documented enough and you don't have a complete specification of what the compiler does, even if we have some part with the on-demand and some formal explanation of what happens inside.
yeah, I think a formal specification, even if it's complicated to read, etc., would be probably very interesting to do. And having the formal specification, having maybe some toy implementation in different languages would be also useful. And I think obviously an implementation in Haskell. And
We had that at the beginning of the first project. Using the clean language, which is
died.
language, it died probably, and it was a way to have a quite clean implementation of the compiler. But the thing is that the efficiency of the compiler was not good enough, and so at some point everything was written in C++. But then you go into other kind of problem when you want to master C++, and you lose in some way the essence of what the compiler is supposed to do, because everything is mixed into details of the implementation language. So this is a real problem for us to, I think, because only Jan and myself we know what happened to the compiler, and if you don't find someone to help you on the compiler, then what happens when you work on the compiler anymore? more, maybe someone can still compile the compiler, but then everything just stops. So this is, I think, something we should try to address.
So on this, we were talking about continuous refactors to improve the way we work. And one thing for onboarding is actually like making small refactors, easy refactors, and pairing with someone who has the knowledge is a very good way to onboard people, even in big companies. That would be one way.
Okay, good idea. So if we create this association non-profit organization, who would like to participate? So Dario and
Why not? It depends.
no, just to have an idea. If I think that
maybe there will be a core group and then a set of participants, which may be very large, but what is important is to probably figure out who will be the I don't know 5-6 members who really think about how we should do it.
And even so, it's a C++ standard. You have different working groups, and for example, there is everything about the language and everything about the library. It's W21 and another one, and this is already so different that having this separation is probably a good thing. You still need them to communicate at some point, of course, but yeah. So having different core teams that can meet to talk about features or to put them, but already this is two big tasks, like one library, one core language. So it's really big.
Well, I guess in Faust we have core language, library, and what we call ecosystem, which is all the tools around which are not directly related to the language, but more.
Yes. Okay, it's still not very clear to me what we should do, but okay. Well, we should do something. Yeah.
What I was thinking is that the members pay for the fee, and the money will be used to start like a small project that is finalized to train some already skilled programmers.
Okay. Yes.
So like this person was saying that I don't know his name. This refactoring together with someone who knows.
Raphael did say that.
And so refactoring and then documenting everything.
We had an idea of documenting the compiler from this IFC version, but it did not succeed. But I started to do that by doing interview with Jan and trying to write
Well, I do very clear and very nice specification, Stefan. I don't know what the point of interviewing. Yes. Sure.
Yes.
Okay, so
There is Alain Bonardi who said we have to find a balance between computer science and computer music within this association. That's what.
Okay, yeah, it's a good point. Yes, it's going also an association of users, and some of them are really musicians and artists, and that's obviously important. Yes. There is also all the question of domain names and etc. that you have to pay, but you have to control also. And if you have Faust.org, well, Faust.org is just impossible to have, but Faustlang.org and this kind of stuff. So the association should have the finance to pay for that. It's not very expensive, but.
But I mean, for this kind of expenses, we can probably rely on INRIA or or whatever. What is really expensive is to pay engineers.
Yes, sure. That's few euros per year, so it's okay. Yes. Okay.
I mean, the work that you do in maintaining the compiler is really expensive. So as long as you do it, we can structure the Faust community in a different way. But
as soon as we have to pay for someone to do that, yes.
Yeah.
Is this like
externally from Gram to maintain the compiler?
I don't know. I mean,
Couldn't they just be hired by Gram? Is my question.
yes, but this is it depends of Gram, obviously. So you currently Gram started. We started the project at Gram in 2002. So for 20 years, Gram founded the project. Basically, now there are other peoples, but that's not necessarily always the case, and so we have to think about that also. Okay. So the last topic and was to discuss of the what was the last topic? Yes, the future of Faust as a language. So we said a lot of already some points that we would like to develop. Are there other points that we didn't mention and you can think about? So yeah, yesterday we had discussion, or 2 days ago we had discussion about the fact to what's missing in Faust, in my opinion. For example, the fact to be able to modulate. You create a nice effect, for example, with its user interface, etc. But the point is that once you have this component, you cannot modulate any of the GUI parameters. You have to control them by the GUI parameter. So I think it would be interesting to have a method to abstract some of the GUI parameters that are already inside the code without having to rewrite the code, and to be able to control them externally. So it's a feature that would be quite similar to the fact that you have VC controls in a modular synthesizer. But at the language level, basically this operation would be to say, okay, I have this piece of code. This piece of code is using this slider. Now I would like to create a new parameter for instead of these sliders that I can control externally, but without having to edit the code itself. So I'm not sure I'm clear, but
or even you could have like a very complex effect and you want to do just macro controllers. Having just 8 knobs that controls everything into this graph, having them set expressions to do that. How do you do that?
Yes, for example.
And yeah, and the fact, like you said, like without modifying the existing, because it's always possible if you just copy paste code.
Sure.
Currently, you can do it with OSC, for instance.
Yeah.
I wasn't sure about that.
Yes, but yes, okay, sure, you can do it with OSC. You have to but to externally control your program. But let's say that you are writing a Faust program. You want to make a demo, for example, and suddenly you have this nice piece of code written by Dario, for example, and it has a slider. But you would like to see what happens if I control this instead of the slider. I put an oscillator and I modulate this. You can't do that right now. You have to edit the code. It's not necessarily difficult, but it's boring not being able to do that from the outside. To say, okay, I don't touch this piece of code, but I want to control what's inside, controlled by a slider, for example.
So it's like it becomes like an abstract variable.
Exactly. We want to abstract somehow the yes.
But is it that you want to see the effect of the oscillator on the slider?
Sorry?
You want to see the effect of the oscillator on the slider?
Not necessarily. At least you want to see the effect of controlling this parameter with the oscillator instead of a manual slider.
So it's like, for frequency you can submit like a fixed number, or you can submit like, a signal, or depending on different arguments you can
it depends. If you control it with a control rate signal, it will be again control rate. But if you control it with oscillator, it will be because we don't care, because in Faust the control rate is just a decision of the compiler to see things involving only sliders and constant to be control rate, but it's not part of the language, so to speak.
But, I mean, it will not be the same as replacing the slider by an oscillator.
It should be the same.
No, because this is at sample rate, while in the first case it's at control rate. So you miss some samples.
In what I propose, it would be like taking the source code, replace the slider with an oscillator, but without having to edit the code itself.
It seems to me that in for instance for XPGA we have two codes, control code and they are not executed at the same rate. So if you
No, but we are speaking of the Faust code itself. It's not, we are writing Faust code. What I'm saying here is that we are within writing Faust code. It's not that we want to control and externally compile the Faust code. Just in the process of composing components, etc., in the Faust code.
Oh, you don't want to reuse a component that has been compiled
No,
and control it?
No, it's just to reuse uncompiled Faust code, so to speak, but without, yes.
Maybe we can give a concrete examples so people, I mean, what was suggested, for example, I think that was your suggestion, to put a wrapper around something that already exists with a parameter that you transform to an input of this new module. And you could do this for every parameter. So you lose names, so it's positional, but at least it's there, and it's then just like a block you can use in Faust. That would be one way to do it. Do you think about other ways to do it? That, yeah?
No, basically it's to instead of it's remote controlling a piece of Faust software by another piece of Faust software inside the Faust program. So it's not compiled. Yes. Yeah, I understand. If the code would have been compiled, then it's different, obviously. Yes. Okay, so we should.
So I was when you during your talk that probably the ones the on-demand directive will open many new directions, like FFTs, and using it efficiently, using when it's working, when it's not working. I mean, a concrete study about what we can do with that should be done by the Faust team in some sense.
Yes, hopefully we expect that with the same on-demand technology, so to speak, to have all the others extension I mentioned, because they are basically the same. So we will have real multi-rate in this. But
if you have multi-rate, if you have you can do much easier frequency transformation and so on, and we miss that from my experience.
Yes.
It was not very easy, and probably it will even grow, increase the number of applications.
Yes. There are several remarks in this direction saying, okay, Faust is nice, but we need FFTs.
There is Jean-Louis Paclin who say you may add a new process-like variable for some or each UI.
To add
to add a new process-like variable for some or each UI.
I'm not sure that. Basically, what I see is to be able to say, okay, I have this piece of code. I know that in this piece of code there is a slider called volume, and I say, okay, let's abstract volume from this piece of code. And now this piece of code has a new entry that replace everywhere volume was used inside this piece of code is now a new entry. And so I don't know if that answered the question to.
Because yeah, it's another way we were talking about was to say calling a function with and then replacing in the lexical scope of the function that is called, placing the literal string to replace by a false expression.
Yes, I think we can just, without saying by which we replace, we can just abstract that. It's a new input, and then by connecting.
So either that or
yes. And I think that we don't even have, because we were thinking, okay, in a modular synthesizer, you still have the knobs, but you have the voltage control, and there is a smart way, depending on the type of parameter, to combine the knob and the voltage control. It's added if it's pitch, for example.
Second knob to
you have a second knob, etc. So we should be able to do this kind of stuff. But I think that if we have this way to abstract the slider volume, it's a new entry, a new input to the resulting code, and then you can just say, okay, now from the outside, I reconnect a knob called volume and do some more processing, etc. So you don't have to put the function. It could be as soon as you have the entry, the new input, it should be enough, I think. Okay, so any other question?
Yeah, can you connect to the chat with your computer? I mean, it's hard to.
So I should go to what's the
on YouTube? It's SMC-22, and you will find the
live stream.
Yeah, if you can see the chat because there's some structure. Yeah.
Okay. Okay. Like process equal volume equals some LFO. Okay. So I should answer on the chat. So basically my idea is that you have P, and then from that you say lambda, lambda, I will give you some example by mail. Okay, Jean-Louis, thank you. Yeah. Anyway, we should discuss this kind of questions, obviously. I think it will be a nice addition to the language. Okay, so I think we should stop now, and we have to go to bring some equipment to Telecom, and we have to go to the inauguration of SMC. So yes. So thank you everybody for coming. Thank you for people in the remote on the live stream. And we don't know if we will have IFC in 2 years, but we hope we will have a new edition of IFC, obviously. And I think I was very happy to see the evolution of things in terms of the blend between theoretical contribution and practical contribution and musical contribution. I think if we can go with these three legs, it's super interesting. So yeah, I think it was nice for that. Xiong is here. Hi, Xiong. Okay. Thank you.